In section 18.3, we looked at limits on the size of things like buildings and mountains. In this section, we're going to focus more on living things, plants and animals, and see how big they can be. So first, what about movie monsters like King Kong? Is it possible to scale up a gorilla to the size of King Kong? One thing that we can look at is whether or not a gorilla that size bones would support its own weight. And the resistance of bone to crushing is 3.7 million pounds per square foot. Now that seems like a lot, but the area of bone that is supporting the weight is actually relatively small, and the center of bones, like the femur, contain bone marrow which has almost no resistance to crushing. So we've got all that weight, and it's basically supported by just the outside ring of bones like your femur, so there's not very much area holding that all up. Various sources suggest that it might be possible for an ape as large as King Kong to exist, but it would probably have a hard time moving around. When animals get that large, they need to have special adaptations to help them survive. So maybe you could make an ape that big, but it probably would have to be significantly different than your average gorilla. Let's take a look at the example of a tree and see how tall a tree can be. Galileo suggested that no tree could grow taller than 300 feet. The tallest known tree today is a giant sequoia, which is 379 feet tall. So it's a little bit off, but maybe pretty close. And we're going to ask ourselves whether there can be a mile-high tree. So we have to consider several things here. First, the wood at the bottom needs to be able to support the weight of the tree without being crushed, so we need to look at the crushing strength of wood. Since a tree is a living thing, there are also going to be other considerations. The tree needs to be adequately anchored by its root system so that it doesn't fall over or blow over with a strong wind. And it also needs to be able to get water and minerals from its roots up to the top, to the leaves. So first, let's estimate the pressure at the base of the tree due to gravity. And we're going to model our tree as a cylinder. This is not a very accurate model of a tree because we're just going to make our tree essentially be a pole, so it doesn't have any branches or leaves on it. And we're looking at a tree that is 1 mile high, or that's the same as 5,280 feet. So you can measure that 1 cubic foot of wood is going to weigh about 32 pounds. And over each square foot at the bottom of the tree, there's going to be 5,280 cubic feet of wood, since the tree is 5,280 feet tall. So since this is a cylinder, each square foot of the bottom of the tree is going to carry the same amount of weight. So if we want to find the pressure, we know that pressure is equal to weight divided by area. So we'll just look at the weight over 1 square foot of the bottom, the base area of the tree. So over each square foot there are 5,280 cubic feet of wood, and each cubic foot of wood weighs 32 pounds, so the weight is going to be 5,280 times 32 pounds. And if I put that into my calculator, I'm actually going to round this, so that's going to give me about 165,000 pounds per square foot of pressure at the bottom of a mile-high tree. So can the tree support that much weight? Well, it turns out that the crushing strength of wood is about 70,000 pounds per square foot. So over that amount of pressure, the tree would begin to crush under its own weight. And the pressure that we calculated for our cylinder model of a mile-high tree was more than twice that, so that would definitely not be able to exist if the tree was just a cylinder. If instead we had modeled the tree as a cone that tapers up towards the top, then the pressure at the bottom of the tree would be significantly less. That would be about 55,000 pounds per square foot. So that would be a tree that's a cone instead of a cylinder would look more like this. This is still not a very good model because it doesn't have any branches or leaves, but maybe a little bit more like a real tree. So if we have a conical tree, that would not be crushed under its own weight. And it would also be possible for the tree to get nutrients from the roots to the leaves. But a mile high is still kind of pushing the physical limits here. 55,000 pounds may seem like it's pretty far off from 70,000 pounds of pressure, but really it's pretty close. And once you consider that there's going to be more weight from branches and leaves, then maybe it wouldn't actually be possible to get a mile-high tree. Researchers actually explored the maximum height of giant sequoias in 2004. They found that as height increases, leaves get smaller, drier, and less efficient at photosynthesis. Based on their findings, the researchers estimated that trees can't grow to be more than 400 to 427 feet tall. So this is higher than Galileo's estimate, but not off by as much as if a tree could actually grow to be a mile tall. The tallest reliably measured tree was a North American Douglas fir, which was measured at 413 feet, so right in the middle of their range, in 1902. Now we're going to talk some about gigantic animals. Animals obviously are much more complicated than trees. They have to be able to move around and do a lot of other things that a tree doesn't have to do, so we're not going to do any examples with animals. We're just going to talk in general about them. So first let's look at how big actual animals get. The blue whale is the largest known animal in history, weighing about 170 metric tons and reaching 30 meters in length. There have been some other giant animals over the course of history, but not quite as big. The largest land animals were sauropods, or long-necked dinosaurs, and scientists estimate that they may have been as big as 100 metric tons, so not nearly as big as a blue whale. The largest known land mammal was Paraceratherium, a hornless rhinoceros-like animal which weighed 11 tons and was 8 meters long. So that's really only about a tenth of the size of those large dinosaurs, and that's the largest known land mammal, which is now extinct. The largest living land mammal is the African bush elephant, which is about half the size of that rhinoceros-like animal at about 5 metric tons. So animals can get pretty big, but why would an animal want to be big? There are some advantages. Bigger animals are safer from predators and also better able to protect their young. They're not as attractive a target for prey animals as some smaller animals might be. Taller herbivores such as elephants and giraffes also can reach higher foliage, so they have a food advantage over other animals that can't reach the top leaves on the trees for food. Metabolism also decreases with size, so giant animals can consume a lot less food as a percentage of their mass or body weight than small animals. And they're also able to eat foods with lower nutrient contents. Another advantage is that large animals are less affected by temperature extremes, So this can help them survive better with a broader range of temperatures than smaller animals. There are also some drawbacks to being giant. First of all, the same amount of space supports far fewer large animals than small animals, so the population of a large species of animal will always be relatively small compared to populations of small animals. While elephants and rhinoceros rely on their size to protect them from other animal predators, size is not a very good protection against human predators or poachers. They can't fly or climb trees or burrow into the ground to get away, so they have a drawback there. One interesting thing is that reptiles have never become gigantic. And one reason why this might be is because they grow relatively slowly. The largest crocodiles can grow up to 1 metric ton, which is pretty big, but they'll take about 100 years to get to that size. So this is kind of a short section, the things that you should know. You should just understand that nature puts additional constraints on the size of living things besides just the physical constraints of crushing strength.